Wait a minute.
Okay.
Right. Good evening, everyone, and welcome to another CAS webinar. Tonight, we have space news from Roy Bryce. Then our main speaker for this evening is Dr. Julian Onions, whose presentation is entitled Crazy Interstellar Rockets. Our next webinar is on the 25th of October, when our speaker will be Catherine Rayner Evans, whose presentation is entitled Exploring Astronomy and Space Through Philately. Eddie Carpenter's wake took place on Saturday, and Bob McWhinney attended and passed on CAS's regards to his widow, and she thanked us very much. Bob said there was some 64 people there, so I mean that was a good turnout, you know, for Eddie's wake. Right, now it's over to Roy for space news.
Okay, so if you give me the usual second or two while I get the correct screen. Hopefully you've got the usual splash screen up.
Yep.
Hey, the last one I did, I played a video and everybody seemed happy enough with it. So this one, because it saves you having to listen to my boring droning on, I've got a couple of videos in it, which I'm hoping you'll find interesting. So anyway, as the regulars know, I'm a big fan of the Mars exploration, and usually there's several slides with the latest news from Mars and my space news for these meetings. Unfortunately, Earth and the red planet are on opposite sides of the sun at the moment. This period, called the Mars solar conjunction, happens every 2 years. The sun expels hot ionized gas from its corona, which extends far into space. During solar conjunction, when Earth and Mars can't see each other, this gas can interfere with radio signals if engineers try to communicate with spacecraft at Mars. That could corrupt commands and result in unexpected behavior from our deep space explorers. This means that Perseverance, for example, has been told to stare at a rock for the next 2 weeks in the hope that some dust devils might pass by and be recorded. Otherwise, nothing's moving. So, since I can't do anything about Mars, I've just read this book, which I must say I found very interesting. It's really the story of the people who had to fight tooth and claw to get NASA to send a mission to Europa to do some really interesting science, rather than spending vast amounts of money propping up American companies, making something pretty useless, also known as the Space Launch System. With Elon Musk's rocket, this is now a bit of a dodo, but nevertheless, vast amounts of money are going to get poured into it. And as the book explains, the only reason this rocket really exists is to keep huge factories in 4 different states in the US busy converting taxpayer dollars into votes for the local senators. However corrupt the system is, it does still mean that NASA continues to be able to fly some very interesting missions. The SLS was planned to be used for all deep space missions, including the launch next week of the Lucy mission. However, since the SLS still isn't ready, this will now launch instead on an Atlas rocket. So here's a short video about the Lucy mission.
The Lucy mission is going to fly past 7 asteroids in 12 years with 1 spacecraft.
We are going to an amazing variety of objects with this mission. And it's really almost pure luck that allowed us to get as many rich targets as we are. Literally, the planets were aligned to allow us to do this mission.
The Lucy mission is named after the Lucy fossil, the Australopithecus fossil that was discovered in the 1970s in Ethiopia. And just like the Lucy fossil transformed our understanding of hominid evolution, the Lucy mission will transform our understanding of solar system evolution.
Trojan asteroids are an interesting population of small bodies that are left over from the formation of the planets, and they lead or follow Jupiter in its orbit by roughly 60 degrees. If you just look at the gravitational attraction of the sun and Jupiter and put something exactly 60 degrees in front of Jupiter, it's stable forever. So as a result, these objects are really the leftovers of planet formation. The stuff that went into growing Jupiter and Saturn are now trapped in these locations.
The very first asteroid we get to is a main belt asteroid named Donald Johanson. We named that asteroid in honor of the researcher who found the Lucy fossil. We're going to use that asteroid to do a rehearsal on our spacecraft to make sure everything is working properly so that when we get to the Trojan asteroids, we're ready to go.
We're visiting both of the Trojan swarms. In the first orbit, we're going into the leading swarm, and we're going to encounter 4 Trojan targets.
Beer babies, Ptolemy, Lupus, and Oryx. And from this, we're going to sample the diversity in sizes, and colors, and compositions. The first 2 flybys happen just about 30 days apart. So it's going to be a pretty busy kickoff to the season of exploring the asteroids in the L4 swarm. And then we'll fly past Earth again and out to the L5 swarm.
The final object we're visiting, which I must admit is my favorite, is a binary object.
So that's 2 Trojans that orbit a common center of mass. It's called Patroclus and Menetius.
These objects are nearly identical in size that orbit one another.
From the Lucy mission, we're going to study the diversity of our targets because that tells us something about their origin and where they came from.
The interesting thing about small bodies in general is they are the leftovers of planet formation. If you look at the 8 planets that we know about, for example, they are highly processed because of internal processing. These asteroids are objects that really haven't changed much from when the planets assembled themselves. And as a result, by studying them, we can figure out the physical conditions of the early solar system, as well as how the planets grew and how they moved around early on.
All of that will help us form a detailed picture of what these objects really look like. Because right now, our best images are just a point of light. Even using the Hubble Space Telescope or adaptive optics on large ground-based telescopes, we can't see surface details. And it's going to take the Lucy mission to go to these targets and see what they're really made of and what they look like.
There you go. Hopefully that wasn't too jerky. I'm never too sure what these videos look like at your end. Certainly works fine here. But anyway, the video didn't mention it, but as it says at the bottom of this slide, Lucy is going to arrive at its first Trojan asteroid on August the 12th in 2027. So provided my flu and COVID jags work okay, I might still be around to see some of the pictures that it sends back. Now, the Colorado Ultraviolet Transit Experiment, aptly named CUTE, is a new NASA-funded mission that aims to study the atmospheres of massive superheated exoplanets, known as hot Jupiters, around distant stars. The miniaturized satellite was built by the Laboratory for Atmospheric and Space Physics at the University of Colorado, Boulder. Small-sized satellites like CUTE, also known as CubeSats, are nothing new. In fact, as you're probably aware, Glasgow is one of the centres of excellence in the world for making CubeSats. They've long been a staple of collaborative university student projects as cheap ways to get engineering experience into space. But lately, researchers have been pushing the boundaries of what CubeSats are capable of, putting them to the test with more and more ambitious projects. In 2010, for example, the first interplanetary CubeSats, Mark A and B, left low Earth orbit and travelled to Mars with NASA's InSight lander, providing communications and telemetry for the lander as it descended towards the planet. CUTE, on the other hand, will remain in Earth orbit, but the scope of its ambition is equally lofty for such a small spacecraft. Its primary mission is to understand the volatile physics around hot Jupiters. These enormous exoplanets have no analogue in our solar system. They're similar in size to the gas giants, but orbit much closer to their stars. They can reach temperatures of over 7,800 degrees Fahrenheit. CUTE's principal investigator, Kevin France, explains, because these planets are parked so close to their parent stars, they receive a tremendous amount of radiation. That radiation heats the planets, causing their atmospheres to inflate and expand. Some of the gas eventually escapes and streams away from the planet. Cube will spend its 7-month mission observing as many hot Jupiters as it can, with 10 as a minimum, measuring how quickly gas is escaping from them. Atmospheric escape is a process that happens on all planets, Earth included, but nothing like as quickly or in such large scales as on these hot Jupiters. Still, understanding how it works in these giants can help researchers understand how it works in rocky worlds too. If successful, the data Cube gathers will be used to understand the processes of atmospheric escape on a wide range of different planet types. This is the first time a NASA-funded CubeSat has been used to study exoplanets. LASP Director Daniel Baker is excited by what these tiny spacecraft can accomplish. As little as a decade ago, he said, many in the space community expressed the opinion that CubeSat missions were little more than toys. There was recognition that small spacecraft could be useful as teaching and training tools, but there was widespread skepticism that leading-edge science could be done with such small platforms. I'm delighted that LASP and the University of Colorado have led the way in demonstrating that remarkable science can be done with very small packages. And now for something completely different, as they say. We've had talks recently about the possible dangers to us of asteroids or comet impacts on the Earth in the future. But here's a story about an airburst event that took place about 4,000 years ago that I thought might be of interest to you all. This might take a second or two to get going. Play.
A new study argues that the ancient Bronze Age Jordan Valley city of Tal el Hammam was destroyed by an asteroid impact. In the same way that the biblical story of Noah's flood could have originated in accounts of the ancient Mediterranean Sea's inundation of the Black Sea, was this the basis for the biblical story of Sodom and Gomorrah? In the Middle Bronze Age, about 3,650 years ago, the ancient world city of Tal el Hammam was a busy, growing commercial hub. Located on the high ground of the southern Jordan Valley, northeast of the Dead Sea, the settlement in its time had become the largest continually occupied Bronze Age city in the southern Levant, with a history going back thousands of years. At that time, Tal el Hammam was 10 times larger than the capital of the Jews, Jerusalem, and 5 times larger than Jericho. The study's lead author, James Kennett from the University of California, Santa Barbara, says this was an incredibly culturally important region, an area where much of the early cultural complexities of humans developed. Tal el Hammam has become a favorite site for archaeologists and biblical scholars. The mound hosts evidence of culture all the way back to the Copper Age, all compacted into layers as the highly strategic settlement was built, destroyed, and rebuilt over millennia. However, there's this 1.5 meter interval in the middle of the Bronze Age stratum that caught the interest of researchers because of its highly unusual materials. In addition to the usual debris you'd expect from destruction through warfare and earthquakes, scientists found pottery shards with outer surfaces melted into glass, bubbled mud brick, and partially melted building material. These were all indications of an anomalously high temperature event, greater than 2,000 degrees Celsius, and much hotter than anything the technology of that time could produce. At the time, Kennett and his research group were building the case for an ancient cosmic airburst about 12,800 years ago, which could have triggered major widespread burning, climatic changes, and animal extinctions. But seeing these charred and melted materials at Tal el Hammam triggered their interest. Kennett says there's evidence of a large cosmic airburst close to Tal el Hammam of an explosion similar to the Dunguska Event in 1908. Tunguska was a roughly 12 megaton airburst of a 60-meter wide meteor over eastern Siberia. The blast was enough to flatten trees into matchsticks over an area of over 2,000 square kilometers, and the flash was bright enough to be seen a third of the way around the world in London. And Kennett was seeing evidence of what looked like similar levels of devastation at Tal el Hammam. The findings, reported in the journal Nature Scientific Reports, showed that the shock of the explosion over Tal el Hammam was enough to level the city, flattening the palace and surrounding walls and mud brick structures. The distribution of human bones indicated extreme disarticulation and skeletal fragmentation in nearby people. Kennett found further evidence of an airburst event by conducting detailed soil and sediment analyses of crucial layers, which turned up tiny iron and silica-rich sphericals and melted metals, both telltale signs of asteroid impact. Just as importantly were findings of shock quartz, sand grains containing cracks that form only under extreme high pressure. This is another clear signpost of an asteroid or comet impact. The authors say the airburst could also explain the unusually high concentrations of salt found in the destruction layer, an average of 4% in the sediment and as high as 25% in some samples. It's thought the salt was thrown up due to high impact pressures of the meteor as it likely fragmented upon contact with Earth's atmosphere. It may be that the impact partially hit the Dead Sea, which is rich in salt, and the local shores of the Dead Sea are also rich in salt, so the impact may have redistributed those salt crystals far and wide, not just at Tel El Hammam, but also nearby Tal Es Sultan, which has long been proposed as a possible biblical Jericho, which also underwent violent destruction at around the same time. And a third city, Tal Minrin, was also destroyed around this time. The authors suggest that this high salinity soil could have been responsible for the so-called late Bronze Age gap, during which time cities along the lower Jordan Valley were abandoned, dropping the population levels from tens of thousands down to just a few hundred nomads. Nothing could grow in these formerly fertile grounds, forcing people to leave the area for centuries. Evidence for the resettlement of Tal El Hammam and nearby communities doesn't appear again until the Iron Age, roughly 600 years after the city's sudden devastation in the Bronze Age. Of course, Tal El Hammam has long been the focus of an ongoing debate as to whether it could be the biblical city of Sodom, one of the two cities in the Old Testament book of Genesis that were destroyed by God for how wicked their inhabitants had become. According to the Jewish Bible story, only Lot and his family were saved by two angels who instructed them not to look back as they flee. However, Lot's wife couldn't resist. She looked back and was turned into a pillar of salt. Meanwhile, fire and brimstone fell from the sky. Multiple cities were destroyed. Thick smoke rose from the fires. City inhabitants were killed and area crops destroyed in what sounds like an eyewitness account of a cosmic impact event. True or not, it's a satisfying connection. Kennett says that all the observations stated in Genesis are consistent in a cosmic airburst, but there's no scientific proof that this destroyed city is indeed Sodom out of the Old Testament. Still, researchers say the disaster could nevertheless have generated an oral tradition that may have served as the inspiration for the written account of the book of Genesis, as well as the biblical account of the burning of Jericho in the Old Testament book of Joshua. This is space-time.
I thought that was quite intriguing. It's a slightly different way of looking at things, if nothing else. So, I said at the beginning of the speech I wasn't going to do any Mars stuff, but I had to get in just one slide. So this is a picture taken from orbit of Perseverance staring at the rock that I mentioned earlier. So back to you, Amanda.
Aye, that was interesting.
I thought so.
You know, that space-time thing, that was really interesting, you know.
Most of the, well, 3 or 4 of the different channels I listened to were running on that story, so I think it sort of caught people's imaginations.
Aye. And I liked the thing about Lucy because I remember you know, reading about the story in Lucy that was found, you know, the bones that were found, you know, and that. So it's always a fascinating topic. I really enjoyed all that stuff. That was really good. Any questions for Roy? We might not be able to answer anything, but are there any questions or? Nope. Oh well, right. Thank you very much, Roy. That was very good. It was very interesting. Right. Julian has always had an interest in astronomy, and after many years as an amateur, studied for a PhD in astrophysics at the University of Nottingham. There he studied studies computer models of galaxy formation using some of the biggest computers in the world, building model universes using mostly dark matter. He also helps out with undergraduate teaching and various outreach activities. So let's give Julian our usual Kaz warm welcome.
Oh, thank you very much. Let me see if I can share my screen.
You should have the permissions.
Does that work? Can you see that?
Yeah.
Yeah. Oh, fantastic. Great. So as a difference from talking about computer models and dark matter and things, I thought I'd talk about crazy interstellar rockets because well, I saw a talk on some of the more crazy ideas for getting people around the solar system and so on a few months ago, and I thought I'd dig into the subject a little more. And anyway, this is what the talk comes out as. So if you want to tour the universe, or at least the solar system, how well are we doing, and how can we improve on that? So the general plan is look at how well we're doing at the moment and how rockets work. That's all very brief, and a bit about how you measure how efficient rockets are. And then we'll jump into the crazy stuff. So the idea is we might well want to go and visit some of these distant planets, the hot Jupiters or the exoplanets we've discovered, or even some of the planets in our own solar system, which are a little difficult to get to, certainly if we want to go in person. So that's kind of the driving force for this. And just to start with, let's see how far we can go and how quickly. So we've got about 5 probes that have now left or nearly left the solar system, and they're doing reasonably well. So we've got the 2 Voyagers, Voyager 1 and Voyager 2, and also Pioneer 10 and 11. And the New Horizons mission, which visited Pluto and now working its way through the Kuiper Belt, but that will soon be out of the solar system too. So the furthest one we've got is Voyager 1 at 152 astronomical units. And you might remember an astronomical unit is the distance between the Earth and the Sun. It's about 93 million miles or 150 million kilometers. So Voyager 1 has gone 152 of those distances. So that's quite a decent way. New Horizons is still at about 50. So, and some of the others are sort of catching up. But they were launched back in the 1970s, or New Horizons in 2006. So they've taken quite a while to get as far as they have. And how well is that doing? Well, the nearest star is 270,000 astronomical units. So we're about 0.05% of the way to the nearest star. And if we actually look at how well these are doing, they weren't designed to go to the nearest star. They were designed to look at the planets in our solar system. But Voyager 1, for instance, will go within a couple of light years of a star within 40,000 years. And Pioneer 10 is perhaps going to get one of the closer ones, but that's 90,000 years. So they're all taking a really long time. And, Pioneer 11 at 4 million years to get close to a star. So these are all very, very long times. And really, we want to do much better than that if we want to go and explore not only our solar system, but our galaxy, I guess. So can we do any better? Right, there's a bit of maths coming up. So either just blank your screen for a bit or follow it through. It's not that hard maths really, I guess. So let's see, how does a rocket work? Rocket is mostly fuel and some payload. The payload might be astronauts or it might be satellites or something like that. And what we're concerned with is this quantity called delta V, which is how much you can change your velocity by or your speed. And you need certain delta V's to get to Mars or to other places. These have all been worked out. And you achieve that by burning your fuel and shooting out an exhaust out of the back of the rocket at exhaust velocity VE. And we'll see that your delta V is very dependent on how fast you can send the exhaust velocity out of the back. So it's basically Newton's third law. For every action, there's an equal and opposite reaction. So it all really comes down to this rocket equation, Telltale's rocket equation. So this delta V, how much can we change our speed by? That's the really crucial thing. And you can see it's very dependent on this exhaust velocity. So the faster you can shoot stuff out of the back end of the rocket, the better your delta V. There are a couple of other things in the equation. The initial weight of the rocket, which is sometimes called its wet mass, which is everything in the rocket, fuel, people, structure and everything else. And the final mass, which would be what the rocket weighed after you've used up all the fuel that you can burn. So it's not quite as dependent on that. It's much more dependent on this escape velocity. Now you can measure rockets in various ways. One way is by looking at the impulse, which is the force times the time. So the force is just how much thrust is coming out of the rocket, and the time is for how long you can do that. So you could measure rockets in that way, but that's not generally how rocket scientists measure it. They measure it in something called the specific impulse, which you might well consider comes from the impulse. So if we take the impulse as force times time, what they do is divide that by the mass of the fuel and also by the acceleration due to gravity, just to get really a conversion factor in there. It doesn't mean they just work at one gravity. But this gives you the specific impulse, and this is really a measure of how efficient a rocket engine is, or at least it's one of the measures of it. And you can view it as saying, how long would 1 kilogram of fuel keep me sustained hovering above the ground? Because we'll see specific impulses measured in seconds. But if we actually just do a bit of mathematical trickery, you can see that an impulse here is force times time. And we've also got force is mass times acceleration, or mass times gravity if we're on the surface of the Earth. So you can actually replace all those things by that. And then quite a lot of things cancel out. So you can see specific impulse is just time in the end. We can also rearrange it to be derived from the exhaust velocity, which means you can feed it back into the Telltale rocket equation, and specific impulse is there in place of the exhaust velocity. Anyway, that's the maths over. One more bit of maths coming up right near the end. So let's have a look at some Isp values and see what's good and what's bad as a rocket fuel or a rocket engine. How well are we doing? If we start with something really simple, we're coming up to November the 5th in about a month or so's time, and look at gunpowder. That has an Isp of 80, so 80 seconds. So is that good or is that bad? You don't really know. I can just tell you it's an 80, but if we compare it to other rockets, at least we've got a basic number. So if you keep that in mind, that 80 for gunpowder, that's what powers the Guy Fawkes rockets. If we now jump to another solid rocket, which is the solid rocket boosters that powered the space shuttle, or at least gave them their start. These are full of something, they're not full of gunpowder, they're full of ammonium perchlorate composite propellant, which is a bit of a mouthful. And they've got a fairly good thrust, but they have an Isp of 242. So that's about 3 times as good as gunpowder. So that's presumably why they don't fill them with gunpowder, because they've got a better fuel. The trouble with these is that they're very much fire and forget. Once you light one of these solid rockets, much like your November the 5th rocket, they will go off, and there's nothing you can do to stop them. They just keep burning until they burn out. So they're usually just attached to the side of space shuttles or space rockets, and they give it that sort of initial oomph to get going. And then after that, it's down to the main engines. Now, if you look at the Saturn V, which was the rocket that took us to the moon, that runs on kerosene and liquid oxygen as its fuel. and has an ISP of 263 to 304. So it's a little better than the solid rocket boosters, and it's also controllable. You can switch it on and off. So the two numbers there, 263 is when it's on the ground, basically, and 304 is by the time it gets into the vacuum of space. The best ones we've got, or most efficient really, are the space shuttle main engines. These run on liquid hydrogen and liquid oxygen, and they have an ISP of somewhere between 366 to 452, so even better than the Saturn V. But again, you know, they have two numbers, one for on the ground and one for up in space. So if we just put all those on a chart, you can see there's gunpowder, there's the solid rockets, there's the Saturn V, and the kerosene. I think I got that number wrong. And here's the space shuttle main engines, and in the vacuum. So you can see there, we've got better. We've got a lot better than gunpowder, but you know, not hugely better. About 3 to 4 times as good as gunpowder is our rocketry. And these green bars are the thrust per engine. So often you need several engines to get you where you need to be. But if you compare that against other things, such as an aircraft, and they don't usually measure aircraft in ISPs, but you can see there an aircraft is much, much more efficient. It's around 3,000 ISP. So many times the efficiency of a rocket engine. Why is that? It's basically because they're cheating. They're using the atmosphere as a fuel, or at least half the fuel. So they carry kerosene in their wings as stuff to burn, but they burn it in the atmosphere using the atmosphere's oxygen. So in that way, they can cheat quite a lot and get a good advantage. So some people have looked at that. Could we get rocket engines, or at least if we want to go into space, could we sort of cheat and use some of that technology? And that's what reactions engine systems looked at with the Skyland project, which is still going, and they hope to be able to use that. So this is an engine that switches between being a pure rocket in outer space to something more like a jet engine when it's in the atmosphere. So you can see from this ISP that it has a fairly good efficiency when it's in the atmosphere, but as it gets faster and faster, it then has to switch to being a pure rocket, and the efficiency drops down to something much more like we've looked at with the other engines. So that's one idea that has been improved, but you're not really getting very much improvement. Certainly if you want to go around the solar system, even that doesn't help you very much. Something that does help you is electric propulsion. These are much, much more efficient than rocket engines, chemical engines. These are so-called ion drives, and they're done by converting atoms into ions, so stripping electrons off them and then accelerating them with very high voltages. So you have these voltage grids that accelerate the ions out the back, and they get very, very fast exhaust. There, sorry. So these can be extremely efficient and have certainly been used. They use something like xenon gas or cesium gas, and we get ISP values of 3,000 to 10,000, so even better than jet engines. The trouble is they get very, very low thrust. So if we look at how well these do, they're extremely efficient. They only need electricity. The amount of fuel they carry is actually quite tiny, and we have tested them. They've been used on several missions to explore asteroids and other things. But the problem with them is they're very, very slow to accelerate. So if you were to go from 0 to 60, that would take you about 2 days in one of these things. So you've got to have lots and lots of time to move around, but they can do this propulsion for a very long time, which is why they have these advantages. So rather slow. But if you put them on this graph, you can see they are extremely efficient. So one of the things it does tell you is that ISP isn't everything, that just being efficient is not necessarily all you need. If you want to go to Mars, certainly you could use one of these engines to get you there, but it would take a very long time because you'd be accelerating very, very slowly. So with that groundwork done, you were promised crazy freaking spaceships, and here's a few of them. I don't know how good your science fiction knowledge is, but there's 7 spaceships there from various science fiction programs. So I'm going to come back to those right at the very end. So if you want to have a go at guessing or recognizing what each of those is, then do feel free. Now, some of these have used some of the things I'm going to talk about, and some of them haven't. So some of them are quite mysterious what they use. But anyway, we're going to start with the nuclear option. Now, nuclear power is quite a lot more efficient than chemical power, but it does have a few downsides, as I'm sure you're aware. But nuclear options were certainly looked at very substantially for rocket power, because they do deliver a lot better thrust. So the first one is what are called nuclear thermal rockets. So these are just really quite simple devices. You've got a nuclear reactor here, much like any other nuclear reactor, but smaller. So something like you might have on a submarine or a aircraft carrier or something like that, quite a small self-contained reactor. And you pass fuel through it. Now, what does a reactor do? It just gets very, very hot once you remove the controlling rods. It just heats up very, very rapidly under nuclear reactions. And if you pass fuel through it, the fuel gets very hot. So the reactor gets very hot, and it shoots out very hot fuel, in this case, hydrogen, out of the back. And you get a very good exhaust velocity from this. And this was certainly looked at in the 1950s and 1960s under the NERVA program. This is a nuclear engine for rocket vehicle applications. And Project Rover and Project NERVA both looked at these. This here is one of these engines under test. So this is actually a nuclear rocket engine being fired. And can you hear that okay?
Sorry, I can't hear anything with it.
Oh, can't you hear it? Oh, okay, right. Well, that's a bit of video of a rocket engine being tested there. So this is a nuclear rocket engine actually being tested back in the 50s. So if we look at how that does on our chart, you can see it's about double the efficiency of the space shuttle engines. So as a mechanism, it's certainly very efficient. It's say double that. It does have a few downsides, as you might imagine. So the ISP is very good. So it's about twice as efficient, as I said, as the space shuttle. It's relatively straightforward. If you know how to make a nuclear reactor, then just pumping fuel through it is straightforward. So you can pick up off the shelf, if you're a government, certainly you can pick up nuclear reactors or buy them. The problem with them, or certainly one of the downsides, is if you're going to have a stage rocket that has first, second and third stages, you're going to drop some of those stages into the oceans as they go up. So you're going to end up dropping nuclear reactors into the ocean, which is probably not environmentally friendly and could be really bad. So they did do some tests to see if they could survive that. They thought they probably could, but it's probably not going to be a great public relations thing, is this nuclear reactor going up, and what happens if it explodes and all that sort of thing. So that is one of the downsides. And you've also got problems with fueling and handling. You are dealing with radioactive material, so that is certainly slightly hazardous, but I wouldn't argue that it's any more particularly hazardous than dealing with huge vats of liquid hydrogen and liquid oxygen, which also have the problem of going off very explosively if you don't handle them very well. But that's only the first step. You could actually go a lot better than that, still with nuclear rockets, by just cutting out the middleman. And this is designed for Robert Zubrin, who's certainly a NASA engineer at one point. He's had several companies he's worked for. But he said, well, why bother with having a nuclear reactor and feeding fuel through it? Why not use the nuclear fuel as the actual propulsion? So this is his design. It's called nuclear saltwater rockets because you have a nuclear salt floating around in solution. This is uranium bromide here. And in this fuel tank, you have these boron carbide rods, and they stop the fuel from fissioning. So it just sort of sits there, not doing anything too dramatic at this point. And then you pump it out down here into your rocket engine. And at that point, it doesn't have these control rods damping down the reaction. So you get actually a nuclear reaction happening here. It's actually a runaway thermal reaction, not one that will go into a bomb, but one that just burns and burns and burns. So at this point, you've got what would normally be happening right inside a nuclear reactor happening in the nozzle of the rocket. So it burns extremely fast. There are a few issues with it. It burns so hot that it will melt the rocket bell. So you actually feed water down the side of here that soaks up some of that heat and stops it melting. You also have to pump the fuel out fast enough so that the nuclear reactor reaction doesn't actually move back down the tube and sort of ignite all this uranium bromide sitting around down there. So it has to go down faster than the neutrons can move back up and sustain it. So depending on what you use, if you use reactor grade fuel, which is sort of enriched to about the 20% level, you can get 12 meganewtons of thrust or 400 gigawatts of energy and a 66 kilometer a second exhaust velocity, which is certainly not too shabby. But if you're prepared to go the extra mile and go to a weapons grade fuel, which is about 90% enriched, then you get a similar sort of thrust, but you get much more power, 30 terawatts now, and around 2% the speed of light. The reaction exhaust velocity comes out. So if you remember back to your delta V is directly proportional to your exhaust velocity, this is a hugely efficient way to fly rockets. So the good, depending on how much weapons grade uranium you can get your hands on, you can get a very, very good ISP up to 10,000 seconds. So we're now getting into the range of the iron rockets, but now with huge thrust. Again, it's fairly simple design. I mean, you don't need anything. You just have to mix the streams and let it go and just pump it quickly enough. The thing that's not so good is it's a very lively design. You are having this sustained nuclear action in the exit part of your rocket, and the output is a highly radioactive. So back in just the thermal rocket, the first one I showed you, it wasn't particularly radioactive because the stuff was moving through the reactor quite quickly and being expelled. But in this case, you've got a highly radioactive mix directly powering your spaceship. So the exhaust is extremely deadly. You don't want to get into the way of that. That's not to say that a Saturn V exhaust is also pretty deadly. You don't want to get into the way of that too, either. The fact that it burns in the nozzle is quite problematic. However, because the exhaust velocity is so high, it's not good for use on Earth, lifting you up into low Earth orbit or something like that. But it's probably okay out in outer space because this exhaust velocity is so high. These radioactive particles are shot out at such rates that they expand very quickly and get very low density very quickly. So this radioactive stuff is just spread out over such a high area so quickly that it's probably no worse than the radiation dose you get from being in space anyway. So providing you're well away from places that wouldn't react well to you giving a highly radioactive exhaust to, it's probably okay. So if you look at nuclear saltwater rockets, you can see they're doing many, many times as the efficiency of the Space Shuttle or the Saturn V. So these are really very efficient things. You do have some issue with getting hold of radioactive uranium in suitable quantities, and especially the enriched sort that you would need for the sort of the extra version with a weapons grade uranium. So these were certainly have been considered. I don't think anybody's considered them particularly seriously so far, but you know, you can't argue with the efficiency of those things. But wait, there's more you can do with nuclear stuff. You can go direct to atomic bombs. What could possibly go wrong there? So this is Project Orion, something that was looked at certainly through the 1960s and probably beyond. And this is based on quite a simple principle that you just let off nuclear bombs. Say, what could possibly go wrong there? So the design is like this. You have, this is a magazine full of atomic bombs up here. This is an absorbent plate. And what happens is you drop your bomb through a little hole in that plate. It goes off. The plate absorbs the impact of that huge detonation. And there's a lot of springs and other things, and it pushes the rocket, or whatever you want to call it, up, or gives it a small boost. And then you just do that over and over again. So you drop more and more atomic bombs out through this pusher plate, and it pushes the thing up into wherever you want to go. So this is a design for it that the Orion project had. You can see the cutaway, and this is where all the astronauts live, a long way from the exploding nuclear bombs. And again, it was tested. You can see this is some of the footage from it. This is done with conventional explosives under models, but you can see there you just have many explosions, one after another, each of them giving it like a definite push up into the air. And I guess they were saying, you know, there you go. If you just give us a load of nuclear bombs, we can do the same with a rocket and get you up into a low Earth orbit. Now, we all know nuclear bombs are not very environmentally friendly, to put it mildly. So why did they actually look at this? And when you see the reasons, you do start to wonder if there is not somewhere on Earth we could actually use to launch one of these things. Because here's the Saturn V. It can get 130 tons of payload to low Earth orbit, or 2 tons to the moon. So that's why, if you ever go to the Science Museum and look at one of the lunar landers, you can see what a flimsy craft it really was. And you know, the reason was because the Saturn V, with all its might and power, could only get 2 tons really to the moon. So they haven't got a fantastic launch capability. You know, it's much better than nothing, but 2 tons is not great. If we look at the Orion project, you can see they're actually smaller than, at least in stature, than the Saturn V. But if you look at the statistics, and they had quite a range of them. So this is the lunar version. This would have 800 bombs to get it to the moon. It could get 300 tons into low Earth orbit, but 170 tons to the moon. And that is quite phenomenal, you know, compared to this huge Saturn V, which can just get you 2 tons. You can take, you know, a bath, a shower, an exercise room, you know, as much food as you want, a chef. You can take all sorts of things with, you know, 170 tons. That is enormous amount of payload that you can take. You can take factories to the moon to land. But that was the smallest one. The Mars version, that could get 1,200 tons to the moon, or 800 tons to Mars. So this is somewhat better than even Elon Musk is looking at the moment. So, you know, 800 tons to Mars, you can, say, take an entire workshop to build rockets and whatever else you want. Now the Jupiter version, that could get 5,700 tons to the moon, or 1,300 tons to Jupiter. So they have a prodigious capacity to lift stuff off the Earth and into Earth orbit, at the cost, admittedly, of making it completely uninhabitable wherever you launch from, because you are going to launch with lots and lots of atomic bombs. But that's not where they stopped. They said, well, okay, we can get these things, but what if we go all out? What if we built the biggest thing we could think of? And that was the Super Orion. And this has an 8 million ton weight lift. So this could get 8 million tons into low Earth orbit. At that point, you're talking about lifting a moderately sized city into Earth orbit. So, you know, the sky really is the limit there. You can take what you want up into Earth's orbit with these things. They also looked at another version which was sort of optimized for traveling across interstellar distances. So this was the Momentum one. This had a shoddy 400 million ton weight lift, but it could get to about 3% of the speed of light. So at this point, you could get to Alpha Centauri in about 133 years. Still not great, but you know, it's better than the 400,000 years that the Voyagers would take. So at this point, it's starting to look quite realistic that we could actually do something. Okay, nobody who left on this ship would actually get there alive, but maybe their children's children would. So what's the good? We've got very good ISPs from these. If you can build nuclear bombs, you need quite a lot of them, but if you can do it, it's fairly straightforward. You know, we do unfortunately know how to make large numbers of nuclear bombs, so they could be put to use. But the overriding thing is this huge lift capacity. You can just lift up so much mass that it's not a problem. You don't have to make these flimsy lunar modules. In this case, you can make them out of cast iron or whatever you like, basically, because you know, it's just not a problem. But the not so good things about it is obviously the nuclear bomb. You are going to make a wasteland of wherever you launch it from. Very, very radioactive output, obviously. So I guess that's why they didn't consider actually using them in anger. However, you know, there are some uses for these things at a pinch. If we find an incoming asteroid is coming in and it's big enough to wipe out all life on Earth, then, you know, this is the sort of thing we should go for. We should build a whole load of these. You know, if we can build them in enough time, the Earth is going to be destroyed anyway. But this way we can get lots, you can get a substantial number of people off the Earth fairly quickly, together with lots of other things. So, you know, as a last resort, this is still a possibility. Now, if we switch gears and go from sort of atomic or nuclear stuff based on fission power, we go to fusion power. There are other possibilities. So this was a concept looked at by the British Interplanetary Society. Could we go to the nearest star? And they said, yes, we could, but we're going to have to use fusion power to do that. And we're going to have to build a stonking big ship. And this was the size of it. So this is Project Daedalus. I think these are fuel tanks all around here. This is the fusion engine, and right up at the top is the living accommodation. So this works on having little pellets of fusion or materials, and this is helium-3 and heavy hydrogen. So you make little pellets that are about the size of marbles or something like that, and you drop them into the reaction chamber. Then you hit them with these electron guns, and they heat it up and compress it. So you get a small fusion reaction there that's enough to power, or at least give the rocket a sort of bump. But you don't just do one of these, you do several a second. So you have a continuous stream of these coming into the reaction chamber, hit them with the electron gun, and you get a power from it. This would be the overall, what it looks like. It weighs an enormous amount. So it's not something that you could use to lift off from the Earth. You would have to build this in low Earth orbit. So the good, you could get up to about 12% of the speed of light. Again, quite efficient. It weighs 54,000 tons, of which 50,000 tons is fuel. So Yeah, that's just 4,000 tons that your payload could be. And they were looking at going to Barnard's star because at the time in the 70s, they thought that had a planet at least. So it seemed a reasonable place. It's not quite the nearest star, but it's amongst one of the nearest stars. And Alan Bond, who is behind the Skylon project I talked about a few slides back, was one of the designers of this. So it's very, very large. You're going to have to find a way of building something like this in Earth orbit, probably mining asteroids or something like that and fabricating it in Earth orbit. You certainly don't want to lift 54,000 tons of stuff up into low Earth orbit. And there's better targets now. We know there are planets around Proxima Centauri, so that would be a better target these days. And they did have a follow-up with Project Icarus to look at other concepts. Another concept is if you don't want to take all that fuel with you, you could actually pick up the fuel on the way. And this is the Buzzard ramjet. So a ramjet works by scooping fuel as it goes along. So it looks something like this. You have a huge scoop at the front, which collects hydrogen as it goes along. It's filtered down and burnt in a fusion reaction at the end. And this is the concept that, empty space is mostly empty, but it's not completely empty. And if you're going fast enough and you have a big enough scoop, you can actually scoop up hydrogen as you go along. There's just a few atoms per cubic meter. But if you're going at a good fraction of the speed of light, you go through quite a few meters of that quite quickly. So you can actually scoop it up and compress it as you go along. This is the concept behind the Buzzard ramjet, which 1960s Robert Buzzard came up with. And they reckon this could get to about 6% of the speed of light with one of these things. And there are lots of fusion options that were considered for these things. These are just some of them. I particularly like muon catalyzed fusion. I don't know how it works, but it sounds really a fab name. So there's lots of possibilities. The trouble is we've never really done any of these things in a controlled way. The only fusion we've done on Earth is a hydrogen bomb, and that isn't particularly controllable, as you might know. So getting controllable fusion is still a goal. So the good, it's a very good efficient system, up to 10,000, 100,000 seconds of ISP. The design is not too difficult. You just got to feed all this fuel through. Has a very high exhaust velocity. The things that are sort of stopping us from using this is, well, firstly, how do you stop? It's all very well, you're going through space, scooping up all this fuel, but at some point you want to stop. And normally you turn the rocket around and use the engine to slow you down. But now you're no longer scooping up fuel. So you're going to have to store quite a lot of fuel to stop you. As much fuel as got you to the speed you're going. So that's tricky. People have looked at other schemes for stopping using this big scoop as perhaps a brake or something like that. Another issue is that we're not in a good place in the galaxy. We're actually in a supernova bubble. So a supernova went off a few million years ago and cleared out a lot of the hydrogen from our neighborhood. So if you're going to be a Buzzard ramjet, it's not the best place to use one of these things because there isn't nearly as much hydrogen floating around our solar system as there are around other solar systems. So that's not very good. And you also need to get up to speed. So you've got to get to a certain speed before the ramjet actually works, before you can actually scoop enough fuel to keep the engine going. So that's an issue. And just in general, fusion is pretty hard to achieve like this, particularly with interstellar hydrogen, which is mostly just normal hydrogen, not the heavy hydrogen, and that's much harder to fuel. So that's another option. Then we got something that doesn't need any fuel at all. This is Project Starshot, which is being looked at actively at the moment. And the concept behind this is one of their animations, is that you take a huge bank of lasers here, and out in space you have this delivery system which has a little spaceship attached to a huge solar sail. And then you turn your laser to point at this solar sail and you hit it with an absolutely ginormous amount of laser power. This accelerates the small device up to a very, very high speed and shoots it off to the nearest star, called Breakthrough Starshot, funded by a Russian oligarch, I think, had Stephen Hawking as one of the members of the team when he was alive. So they're still going strong with this. And this is the sort of thing they're looking at. So this is your spaceship. It's a very, very tiny spaceship. It's basically a sort of just a chip on a circuit board, and has all the stuff you need to get. It has maybe a tiny camera and a little solar power and all the rest of it. So the stuff behind it is quite phenomenally. So it accelerates at 10,000 Gs, which is far beyond the ability for any life form to survive. So it's got to be very robust. It's going to get hit with 1 terajoule of laser power, which is a frighteningly huge amount of power. So just surviving that and not melting is also going to be hard. They give it this 1 terajoule for about 10 minutes, which is enough to accelerate it to about 10% of the speed of light, and then off they go. But the upside is it's very cheap to produce these chips. You can see they're not very big, so you can produce lots and lots of them. So you're probably going to aim them at Alpha Centauri or something and send 1,000 of these at a time. So some of them are not going to survive. Some of them are not going to survive the acceleration. Some of them are not going to survive the journey. But the idea is if you send enough of them, some of them will get through. Well, that's the plan. Whether that is true or not, I don't know. So they don't have an ISP because they don't have a rocket engine in it. They don't need any propellant. All the propelling is done from Earth. Cheap to make, so you send lots. The not so good is I don't know how they stop from vaporizing the chip. They have to be extremely reflective to not soak up any of that laser power. You know, even if it's 0.1% of a terajoule, that gets very hot very quickly. You've also got to go through the interstellar dust, the same stuff that the Buzzard ramjet is scooping up. There's all these tiny bits of dust floating around in outer space. And if you hit one of those at 10% of the speed of light and you're a very, very tiny chip, it's going to ruin your entire circuit board, basically. So they're not going to survive encounters with that. So that's another reason you've got to send lots and just hope some of them do. I'm also not sure how you're going to send data back. You've got that tiny, tiny chip with a tiny solar cell on it, and you're 4 light years away. How are you going to send a radio signal with pictures all the way back to Earth? It's going to have very, very low power. So I don't know how that's going to work. But they do have some very bright people working for them. The other problem is you're going through the target system. So say Alpha Centauri at 20% of the speed of light, you're not going to get many pictures in before you actually pass through the system and out the other side. So you've got to be quite quick on the uptake for that. Now, the final version I've got is to use the raw power of light. So this is actually using just light out of the back. So in this case, you just have a nuclear reactor and you just let it glow white hot and it shoots light out the back. Light doesn't have any weight to it, but it does have a momentum. So you can use this to shoot you going the other way. So these are called nuclear photonic rockets. And you can certainly do it with light. So you can shoot out very bright light from the back. That would be enough to power your rocket. Or even better, you could shoot out gamma rays. You get even better sort of bang for the buck for that. The very good thing about this is you've got the best exhaust velocity possible because you're sending stuff out at the speed of light. And it doesn't really need any fuel other than just to keep the reactor ticking over. The downside is that light is, well, very light. So you don't get a great acceleration for this. So it's quite efficient. Well, it's a bit like the ion drives. It doesn't give you a huge acceleration because you're not getting a huge momentum transfer. So you get very low acceleration, and the exhaust is fairly deadly no matter how you look at it. If it's gamma rays, it's extremely deadly, and you know, even very bright light is quite deadly. So not so good, but it's worth putting on the slide because they have the best ISP of any system going. So if we stack them all up, and I put them on a log scale here, so you know, each one is 10 times better than the previous. So you can see the nuclear photonic rocket has the best ISP, but not necessarily the best thrust. Ion drives are not far behind, but nuclear saltwater rockets are probably the best things for moving around quickly, and Orion drives, so on, are in there too. So that is kind of the end of the talk on rockets, but there is one last thing in the bag of tricks, and that is warp drives. You know, is Star Trek a reality? And it turns out it is, or it might be. Nobody quite knows. But anyway, this came from the brainchild of Miguel Alcubierre, who was a physicist, or well, he was actually a PhD student when he discovered this. So that's Miguel there. He was watching an episode of Star Trek, and you know, said, "Oh, there, this warp drive stuff. I'm working on." He was working on general relativity equations, and said, "Well, I wonder how this warp drive actually works." He said, "Well, I'm in a good position to do this. I've got all the tools at hand. I've got Einstein's general relativity equations. They tell me how you can warp space." So he played around with a few of those things and came up with a warp drive, you know, sort of one night in his spare time. He wasn't sure whether to publish, but he eventually did after talking to his supervisor. He said, "Well, you know, I've come up with this idea. It's a bit crazy. I don't know whether I'll be laughed." And be the end of my career as a scientist, because I've come up with this thing. But he said, "Well, no, the maths looks good." So anyway, he published it, and that was 1994. And indeed, he did come up with a warp drive. And this is basically how he came up with it. So this is the field equations from Einstein. So this bit says how space curves, and this says how matter behaves. And nearly all the science works on taking this bit, which is the matter bit, and seeing how space curves. So you drop a big star into space, and that tells you how light and other things curve around it. Or you drop a black hole into space, and this will tell you what the environment is like in around the black hole. But he went the other way. He said, "Well, I want space to curve in a particular way so that we can use it for a warp drive. What do I need to do over this side to get that to happen?" And it turns out you have to do some fairly dramatic things. So this is kind of the warp drive that he came up with, or at least this is one version of it. And you have to have your strange stuff in these rings around the spaceship. And what you end up with is this thing called a warp bubble. So you have around here, you have unaffected space. So space here is actually almost like normal space. But out in front of your spacecraft, your warp bubble contracts all the space in front of it. So it's very, very squashed up. And behind it, you do the opposite and you expand space. So the space behind it is hugely enlarged. And it's a bit like, trying to think of a good analogy, is sort of like moving across the room by sitting on a rug and somebody pulling the rug. You're not actually moving, but the rug is moving. So in this case, it's not you that's moving, it's space is moving around you. So this has some very neat effects. It means you don't have to accelerate at all. You just sit there and space moves around you. So you can go up to any speed you like, pretty much. And he said you can go absolutely to any speed you like, and you don't have to accelerate. So you don't have this crushing acceleration of 0 to 60 or pulling 9 Gs or whatever. You're just sitting there, relaxing in your armchair as space moves around you. So that's fantastic. the problem with it is, at least in his original design, was that you need some very exotic matter to bend space like this. You need negative energy or negative matter. So this is not matter that weighs anything. It's not matter that weighs nothing. It's matter that weighs the absence of something. So it's kind of like, or energy, and negative energy would also work equally well. So again, that's not energy. It's like not positive energy. It's not zero energy. It's something that subtracts energy. And in his original design, you needed about a couple of sun's masses of this negative energy that we don't know how to make to actually get this warp field to generate. So that was kind of why it stuck as just an interesting idea for a while, because it was completely infeasible to do it. Firstly, you'd have to make this negative energy, which nobody knows how to make, and then you'd have to make a sun's worth of it. But people have tinkered with his design over the years, and in fact, a NASA engineer called Harold White, or Sonny White as he's better known, he tinkered with those equations, and he said, well, actually, he took a rather pessimistic view of it. We can get better than this. We can actually reduce this down, and he reduced it down to about a planet-sized worth of negative energy, and then to sort of a double-decker bus weight's worth of this negative energy. And now it's suddenly becoming almost tractable. Okay, we still don't know how to make negative energy, but if we did, we wouldn't have to make quite as much as we thought. So maybe we could build it. So yeah, if you could, that would be great. This negative energy would go into these rings here and start the warp bubble. And it would all be great, except for a few downsides with it. In fact, there are more than one downside to it. Firstly is, as you travel through space and you actually go faster than the speed of light, your view of the universe collapses down until you just having a look through a very tiny pencil beam directly ahead of you. So you can't see the rest of the universe, which probably isn't too bad, because as long as you're going in that direction, you can actually see what's coming to you. Most of the stuff will be highly blue shifted, probably up to sort of gamma rays and things like that. So that's a bit of an issue. Another issue is that as you're going through space, you tend to build up a whole heap of energy on the front of this warp bubble. It's all sorts tends to accumulate that. So when you drop out of warp, this energy gets freed up from the warp bubble and tends to obliterate whatever you're pointing at that point. So you've got to be a little careful when you arrive in a solar system that you're not pointing at anything that might be expensive or whatever. So that's a couple of downsides at least. There's a few more though, but let's look at the positive sides. It's your best bet to travel across space. You can travel almost anywhere with this device. You can get to Alpha Centauri in minutes or seconds possibly. It's inertialess, so you don't, you can accelerate to any speed because you're not actually going anywhere, and it will actually get you to the next galaxy quite comfortably, providing we can fix some of the other things. So this is fantastic. This is the way to explore the universe, to explore the solar system, to explore the galaxy. Absolutely everything comes within the grounds of this. I said there are a few issues. So yeah, okay, you may destroy the system that you arrive at, but yeah, pay a few damages and that you can probably write that off. It's more tricky is, how do you start and stop this thing? Once you start this warp bubble, you're sort of cutting yourself off from the universe in general. So that's tricky. How are you going to stop that? You sort of have to reach outside this warp bubble to switch it off. People have looked at that and they have some ideas. You might need to sort of arrive at a special de-warpification station that would switch it off for you. There are other ideas around that too. The problem with exotic matter is certainly one of the issues, because we don't know how to make it. And perhaps the most damaging part is that it probably allows time travel. If you can go to Alpha Centauri in a few minutes, it's 4 light years distance. So you've covered 4 light years or 4 years in time in 2 minutes. If you turn around and come back to the Earth, you come back to the Earth as it was 8 years ago. So you've traveled in time. So you've not only traveled around the galaxy, you can also travel in time. And that leads to all sorts of paradoxes. So most physicists think time travel is probably not allowed by the laws of nature because it just seems to generate so many paradoxes. So that might not be quite so good. This warp drive can also let you go slower than the speed of light. You can go at any speed you like. So, you know, if it turns out that going faster than the speed of light is too exotic, then that could be. But firstly, we've got to build one of these things at all. And the fact that you need exotic matter is an issue. Except just this year, stop press, a new paper came out saying these Bobrick and Martier came up with a new physical warp drive that they said, we've taken another look at the equations and actually we can do it with regular matter. We can actually make it with regular matter. We don't need any of this exotic negative energy matter that we don't actually know whether it exists or not. And if it did, we didn't know how to make it. Well, we can actually make one without needing that. So this is another jump forward in the process, that you can now make warp drives with stuff that we do know how to make. They do admit there are still a few issues that you know, we can't just have our warp drives right now, here and now. There are still some things that need to be fixed. But it seems like you know, from the very beginning, where you needed a few suns worth of this exotic matter to actually build something, to nowadays you probably just need regular matter, just a certain concentration of it. These things seem to be getting nearer and nearer as we look into them. Anyway, that is the end of the talk. So just to wrap up, the best way to travel. If you want to get off the Earth in a hurry, your best bet is definitely one of these Orion type spaceships. It's going to make a mess of wherever you leave, but if you need to get off in the event of an incoming asteroid or comet that's going to wipe out all life, this is your best bet. I think currently the best bet for traveling around the solar system is one of these nuclear saltwater rockets. They are highly efficient, and you can certainly go, you know, around the solar system in much quicker time than you can with almost anything else. So that would be my best bet for doing that. You would use some other, you perhaps use chemical rockets to get into low Earth orbit, and then you take one of these to just go flitting around the space if you can't get hold of one of these. But if you want to go tour the galaxy, or you want to look at other galaxies, then these warp drives seem probably the best idea, but still a few issues with them. Now, if anyone wants to have a go at the quiz, do feel free, and I will finish there. Thank you very much for listening. You must be able to get at least a couple of those spacecraft.
Oh, well, on the top row, the far right is a Millennium Falcon.
Correct. Yes.
From Star Wars.
Yep.
Good.
Delta One Discovery, top left.
Top left, Discovery 2001. Correct. Yes. Very good.
Top right, the Liberator.
The Liberator from Blake 7.
Blake 7.
I never watched that, so I don't know. I watched Star Trek, so.
I haven't got Star Trek on there.
No.
Bottom centre is Space 1999 Eagle Transporter.
An Eagle Transporter.
Right.
Yes. Very good. Very good. Anybody recognise this from another science fiction series?
Terrahawks?
No, not Terrahawks, although I can see where you're coming from. Yeah, no, that's actually Serenity from Firefly.
Yeah, I watched that. Yeah.
Okay, yeah. And this one nobody ever gets, and this one I've had a couple of people get. This is also a fairly modern series, and this is from a film.
Is that not something from the Alien films?
No, not from that.
No?
Though, yeah, I should have included the Nostromo. So yeah, Discovery 1 from 2001. This is Antares from The Day After Tomorrow.
Oh yeah.
That's a film with Brian Blessed in it, and they go off to explore the universe in a photon drive. So that's why I included that one. Millennium Falcon from Star Wars, Serenity from Firefly, The Eagle from Space 1999, Liberator from Blake 7, and this is a Leonidas class from The Expanse. If anybody's watched
it was The Expanse, yeah.
No, right, no.
Read all Expanse books, but I've never seen the program.
No,
yeah.
I loved the Firefly movie, and that it was really good.
Yeah, shame it got cancelled.
And the TV series was, you know, it was a shame that got cancelled, because it was really good.
Yeah, very much so. Right, I'll stop sharing and pass it back to you, Alice.
Right, that was really, really interesting. So is there any questions for Julian?
Anyone want to take a trip?
Oh, definitely.
Which one would you go for?
I'm a Project Daedalus man myself, I think.
Project Daedalus, yeah.
There's a lot of possibilities there. And it may not be possible to get that much further and faster, but there's a lot you can do with it. A lot of long-term applications.
Oh, definitely, yeah.
Moving O'Neill habitats around.
And they certainly looked at it in quite a lot of detail.
Elon Musk's rockets, how do the engine in that, how do they compare against the Saturn V?
They're similar to Saturn V in ISP, not quite as good as Space Shuttle. It's because he's using, what did he use? Methane.
Yeah.
I think he uses methane and liquid oxygen rather than liquid hydrogen and liquid oxygen. Mostly, I think, because it's easier to reuse the engines if they've been burning methane. If you're using liquid oxygen, liquid hydrogen, they tend to be a sort of one-use engine, and he's trying to get multiple uses out of it.
It's that book I mentioned earlier on the mission. He goes on about it. It's the space shuttle rocket engines that they've used for the SLS. Presumably,
yes, yeah.
To have the experience of them.
What a waste!
I know.
That really is.
I guess they've got 16 or so left over from the space shuttle program, and after that, they'll start making new ones. Assuming, of course, they ever launch more than 4 SLSs.
Well, quite, yes.
Never actually launch one.
I think they're being taken over by events quite quickly at this rate.
Julian, you may know this, but you can get a book about Project Orion.
Oh, can you? Oh, right.
Yeah, I've got a copy. I'll fetch it.
Oh,
There's
right.
a couple at least. There's one on Project Orion itself, and there's also a biography of Freeman Dyson and his son called The Starship and the Canoe.
Oh, yeah.
Yeah, which is
I know Freeman Dyson was heavily involved in the design, wasn't he?
He was indeed, yeah. And his son designs superboats.
Oh, right.
Yeah. It's surprising how many analogies there are.
Fantastic.
Yeah,
I'll have to get a copy of that
book. Yeah, that's good.
It's called Project Orion by George Dyson, the atomic spaceship, 1957 to 1965.
Yeah, marvelous thing it was. I'll note that down.
$7.99 I paid for it.
Oof.
And that was new. Penguin Popular Science. And there's an autobiography as well there's a biography called Disturbing the Universe, which is about Dyson generally. This is fairly new. I mean, like within the last 15 years. It's not some old-fashioned thing. It's just, as you say, it was written by his son, I think. Copyright George Dyson, 2002.
Right.
I think you should be able to get it on Amazon then.
Yeah, just have a look.
It's
quite expensive.
Without wishing to get too 2001 nerdy, that they originally considered using a Dyson propulsion system, but Kubrick vetoed it because his last film, Dr. Strangelove, had the world ending in atomic bombs, and he'd done enough atomic explosions.
Right, he wanted something different.
The story goes that is why the ship that the shuttle that takes Floyd to the space station is called an Orion.
Oh, really? Oh, right.
So the story goes.
And you can get a model of that too.
It's an Airfix. It's an old Airfix one.
Yeah. Fantastic.
I love model. I've got a model of Liberator too.
Oh, you got them all.
Oh, aye. Yes.
Saw a kit of Discovery in Wonderland Models in Edinburgh last week, but it said it was 15 inches long. The sphere was about the size of a ping pong ball. And it was 84 pounds.
Ooh.
Oh, no, sorry.
No, maybe not.
I'm going to pay 84 pounds. I want something a meter long.
Yeah, absolutely.
Not 18 centimeters.
God. No.
Discovery's engines were gas core fission engines, which seems to be coming back a bit. The British Interplanetary Society had a paper in one of the recent issues about feasibility of it.
I copied the Daedalus study too when it first came out.
Oh yeah, you can get that again now. They've done a hardback book of it, which is prefaced by Shepard's original paper about multi-generation space arcs, which is pretty good, and it's got some extra illustrations in it as well from Matt Irvin and other people. So you can buy that from the BIS, quite a reasonable price.
Right. Another one to look out.
That's worth having. Yeah.
Yeah, I mean, I got the paper version in, I don't know, back in the 70s, 80s maybe.
Yeah, I got
it. It's A4 format, about as thick as my finger.
Oh, right.
Produced to be in the same format as the Project Cyclops report on the giant radio telescope complex.
Got one of those as well.
Billingham must have a big office.
Billingham, who was the project scientist on Cyclops, sent me a copy. And actually, Julian, I've just been told I've just had to move out of my office at ROE, and the first thing I did was I went to IKEA and bought 2 more bookcases. Put them in my spare room.
You can't have too many bookcases.
That was absolutely excellent. That was really good. Absolutely. Very, very good. Really liked it.
So what fuel is it again that is going to lift William Shatner up?
Oh, that's Blue Origin.
Origins,
yeah. I read it. I read about it, and because apparently he's quite nervous right enough. Anybody would be.
Yeah.
But at 90-year-old, I mean, he's game.
Yeah.
Going up there and
be the oldest person in space.
Aye.
Well, just into space.
Aye. So is it just going to the edge of?
Yeah, it goes to.
Oh, right.
Up and down, but it does cross. It does cross the Kármán line, so technically they are in space for a few minutes, unlike the Virgin thing, which I don't think gets to 100 kilometers.
No, it doesn't quite.
Right. Okay.
But it's only like a 4-minute flight.
Yeah,
it's about 10 minutes overall, isn't it? Or something like that.
Aye, something like that. They said,
just like Shepard's flight on the first Mercury, straight up, straight down.
Straight down, yeah.
Right.
5 minutes under the parachute.
Yeah.
Aye.
I'll go. If you're listening, Jeff, I'll go.
I'll take either.
I mean, it's really brave of him, I mean.
He's 90. What's he got to lose?
I know that's true. Well, true.
90 and rich and horribly overweight. What's he got to lose?
Yeah,
I know. Because he's really, I don't know, he's so overweight. I'm surprised.
Somebody else waving something at us.
Oh, yeah.
It's the new Daedalus book.
All right.
Which is available from the British Interplanetary Society, quite a reasonable cost. In fact, they sent me an offer to get that and a whole bunch of other books for a special price. So I grabbed it. It was only about, I think about £25 for the lot, including this. And as I say, there's there's some new stuff in it, and also some classic old stuff. Reproducing Shepard's paper is very good. But
if we're doing boys and toys, there's the original one.
Oh,
yeah,
fantastic.
And there is Project Cyclops.
Ah, yeah, right enough.
Right.
Not only have I got these things, but I know exactly where to put my hands on them.
I know, that is your filing system is second to none, I have to say.
Couple of pages of new artwork by Matt Irvin, particularly illustrating the Warden's concept. So I'm gradually building back. When Linda and I attempted to move to Ireland, I donated my entire library to the University College Cork, so that I would still have access to it. Now they've got it and we're back. So I've got a long way to go to rebuild. But I'm working on it.
Yeah.
By the way, Duncan, I've got one of yours.
Yeah, I've got that one as well.
Yeah.
Yeah.
Illustrated by Ed Buckley and Gavin Roberts. Ed is sadly no longer with us as of a couple of weeks ago.
I know, it was a shame that.
So my obituary will be in the December issue of Spaceflight. Getting down to finalising which paintings they're going to use. But some of the ones out of New Worlds for Old will probably be appearing with it. Yeah, I'm up to 10 books now, but
all right.
Yeah, it's still working, still going strong.
Going strong.
Yeah, I've got several possibilities in the pipeline.
I don't know how many books I've got, but I've got loads. I've no room for any more.
I can always fit another book in somewhere.
No, I don't think so. I've got that many. I mean, I'm reading a book to my friend Henry just now on a Sunday. Dark Dreams about serial killers. So, I mean, it's very good. It's very good. So,
behind you.
I know. Oh, well, hello. Can I interview you? You'd be handy for my forensic psychology degree.
Oh, yes.
Can I interview you? Yeah. I mean, I don't know. I've got loads because I've got that book, as I say, yours, Duncan, and I've got quite a few Richard Feynman books as well. Because I liked his stuff, because I think it was The Character of Physical Law was the first book he has, and because that was part of one of the modules. I think it was the Matter in the Universe course a way back in '92, and I discovered Richard Feynman, and I had to buy more of his books and more of his books and more.
Yeah.
So I've got quite a few of his books.
His autobiographies are excellent.
Aye.
Yeah.
Oh, yeah.
It's a shame he never got to do the third one.
I know. I mean, he was such an intelligent guy, you know, and he had. I loved these. Surely you must be joking, Mr. Feynman.
Oh yeah, there's some great anecdotes in there.
Aye, and the Leonard Milanov, that's how you pronounce it, book, you know, about Feynman, Sometime with Feynman. That was really good as well. It was sad in places, but really interesting as well. So I thought, right, because I've got his lost lectures and that as well, you know. Found him in a rare book catalogue thing. I think it cost about £15, you know. So I had to have that and all.
Have to have it.
Yeah.
Has to be done.
All right. So any other questions for Julian?
I could mention another idea of Dyson's, which is that you grow trees on comets.
Oh, really?
That's in Disturbing the Universe. And it's a very slow process for interstellar travel, but he calls it greening the galaxy. And yeah, I mean, he reckoned that with genetic engineering, you could modify sequoias or redwoods to grow on comets. And they would reach heights on the order of 10 miles in the microgravity and have a sufficient area of foliage that they could live on starlight.
Guess so, yeah.
Terrific idea. There's an illustration of it in Redpath's book, Worlds Beyond, by David Hardy. And I'm in correspondence about other things with David Hardy at the moment. So I asked him about it, and he didn't even remember it. Oh. And being David Hardy, the next thing was a painting turned up the following day in my inbox, which he'd done overnight. And 24 hours later, he sent me another one. It strikes me as a possibility that having done a book called Incoming Asteroid, I might do another one called Outgoing Comets.
Outgoing, yeah.
So I'm looking at putting together a discussion project. It should probably be online like this. So watch the space. Something may come of that.
I see that's the book. I've got that book.
Oh yeah, that's
Mm-hmm.
Oh, is that Richard Feynman? Yeah.
Yeah. Richard P. Feynman and Stephen Weinberg. It was the Dirac, the 1986 Dirac Memorial Lecture.
Right, yeah, because that's Dirac, isn't it?
Oh, sorry, is it?
I think it wasn't Feynman.
No,
I think that's Dirac, I know.
Oh, I saw it. Yeah.
Yeah.
Yeah. Aye, because Feynman's.
Yes, that looks more like Feynman.
Yeah. I don't know where I was. I was thinking. Aye, I forgot that Feynman was in the Untitled. Yeah, but I've no read this for a long time, right enough. But it's a really good book. I've got quite a collection, and I bought another rock sample as well. Shallon blend.
Don't know that.
At One Lockhead. Hold on. I'll need to take these out.
I'll say good night, Alice Amanda.
Oh, good night.
Good night. Great. Thank you very much,
night.
Julian. It's a super talk. Really enjoyed it. Thank you.
Right. Speak to you again, Lynn.
Okie doke.
Right. See.
It's a nicely polished sample. It's good.
It's lovely. It's from I'm maybe not pronouncing it properly. Shallon blend.
Sure, can't read.
It's from Poland. It's got a mixture of sulfurite and wurtzite.
Oh yeah.
But I got it at the mining museum at One Lockhead at the shop for £9.60.
Oh, that's nice.
So it's quite a fair size. You know, as soon as I seen it, it was in the glass cabinet. And I says, oh, I have to get that. That looks really nice. You know?
Because I've been meaning to go back there because they've just doubled the length of the mine that you can go into.
All right.
So they've been working on that during lockdown. So it used to be you went in, you sort of went in a couple 100 meters, but I think it's now up to about 400 meters or something. So it should be more fun.
Because my pal Lawrence, he would like to go down the mine, you know, and there and have a look and just to see what it's like and that, you know. But there's no way I could go down. You know, it's no wheelchair friendly. But they've done it. They've got a nice wee cafe there and that as well. Just had a cup of tea in the cafe and but the Menop Pass, I mean, it was Baltic that day we went. No last no last Wednesday there, but the Wednesday before, and it was Baltic.
I've been there a
like
few
a
times
wind.
because
Aye,
you can mess
like a
about
wind
in the
tunnel.
mine tailings and find quite a lot of stuff. And it's just lying there to just dig through it yourself. That's some quite interesting bits and bobs.
Aye, I mean it's like a wind tunnel, you know, along the Menop Pass. I mean it's because he got out of my car and he stopped the car and he got out and went across the road to look at those like the information post things. They're like a cairn, but the information post. And he was near standing out, he came fleeing back in. He says, "It's Baltic out there." Oh my God, it's Baltic. I says, why do you think I wanted you to put the engine on so that I could turn my window up after I took a photograph from my mobile phone? My horn was gone numb.
You forget just how high up you are because it's not very, very slow.
I know. Oh God, because he saw a picture on, I don't know where he's seen it, I think it must have been online somewhere, but seemingly there has been like rubbish left there and human feces. You know, I mean, it's disgusting. You know, people, I mean, people are, I think because they can camp up there and that, but when you're in the car, so you're not seeing any of that, but people have been complaining about the rubbish and that's been dumped, and I mean, all we seen was a load of sheep and that. And so a bit of rain.
I'm going to have to drop out as well, but
right.
Great lecture, Julian.
Thank you very much for coming. And,
I did one on some of those topics back in the mid 70s, and there was an American kid in the audience who came up to me afterwards. He said, "Ralph Nader couldn't have done it better." So I think you're a worthy successor there. Enjoyed that. Okay, I'm off now.
Right,
me too.
okay.
Nice.
Cheers all.
Cheers everyone.
Right.